All right, can everyone see my share screen? Good. All right, thank you. Cool, awesome. So yesterday we talked about neural network, we talked a little bit about code, and we hit upon the convolution operation. So today the game plan is this. We're gonna start doing a little bit of whiteboarding session of what convolution operation means, and introduce a couple more operation or a couple more layers that serve as a building block, and you guys can play around with basically how that how these operations look like. And then when you guys get to the code, which I'm gonna just talk a little bit, it's not that hard. I don't think I will need an hour, but hopefully I will be able to finish maybe somewhere in the middle of the second session. So that's gonna be when Sam put you guys all in the breakout room, and we're gonna get started on the project ASAP. And the goal is to essentially shoot for Friday so that everyone can have a presentation ready. All right, so let's get things started. First of all, let me do a small recap. I can just maybe go up here. All right. So what's happening here is this. Let's do a quick recap. So neural network, of course, the first building block, the first ever milestone that you have to understand, right? It's called artificial neural network. It's a very simple process. You have some sort of X, that's going to be your data. You send that into the model, that's going to be some sort of magical function, right? You call that F. And then you build output. So output is going to be a Y. And based on what you're doing, right? And this is different for everybody, right? Depending on different data sets. Y can be continuous, that's a regression problem. If Y is in different levels, categorical variable, discrete variable, you name it, right? Their numerical value doesn't have any mathematical meaning, right? 2 star doesn't mean I like movie twice than Sam does, right? If he gave it 1 star. So if there's no numerical meaning, it's categorical variable, then you're doing classification. So this essentially this whole thing we check, right? We've talked through that 2-3 times. Hopefully everyone should be on a first name basis. And if I say something, hopefully you guys understand and can recall the memory of what that is on the intuition level. So that's where we are right now. Okay. So today we're gonna talk about convolutional neural network, and then we're gonna look at the code. Hopefully tomorrow I can jump ahead and talk a little bit about recurrent neural network, and we're going to give you all the basic building block of how computer process language. Okay, so that's kind of like the big game plan. And throughout the course, we're going to put you guys in breakout room, and we're going to do the projects. So this is where we are right now. Okay, corresponding to the lecture slides, remember the document has 300 pages, right? Corresponding to lecture slides, we are talking about the deep learning chapter. So I believe that's chapter 10, if you want to follow it. So that's the material there. All right, so with that being said, let's get started. So first things first, we talk about convolution operation. All right, so what that means is, let's say you have a picture. Let me write out the title. So this is going to be your convolution operation. All right, so assuming that you have some sort of input image, and then you have some sort of kernel. All right, so this is assumed. So of course, you have to have these two things. Otherwise, you don't really have a convolution neural network to begin with. So for those of you who are doing tabular data, I've seen people done this before, although no one has published a paper before, but I have actually seen people done this before, which is if you believe that 2 of your columns in your CSV Excel spreadsheet has some sort of correlation, that you believe that these 2 columns together form some sort of higher order interaction, basically some sort of impact on the prediction, then you feel free to put them together and run convolutional neural network. Okay, I'll repeat that again. What that means is this. So here's a small caveat. Okay, so this is a small caveat. CNN is built for images. Yes, that's correct. And it's not for CSV file. Yes, that's also correct. But it doesn't mean that if I process a CSV file in a grid, CNN will not run. It will still run. It just you lose the interpretation of the geometric shape. Okay, so I'll give you an example. Let's say you have an Excel spreadsheet. This is your CSV or whatever, right? Excel spreadsheet. And then you have columns, right? So maybe that's an X1, X2, da da da. And then maybe this is we're gonna give a strange case, right? Maybe this is like X7. So it's like odd number. You can't even put together in a square, right? So what that means is you have one column here, looks like that, and same here, and then same here. Something like that, da da da, in the middle. And then altogether you have 7 columns, and that's your data, okay? And then hopefully you want to predict the y, and then y is somewhere here. So that's kind of what things look like on the Excel spreadsheet. And then you're like, okay, this has nothing to do with pictures. How do I still do image classification, right? You can still do it, and here's how. So the x1 to x7, it is not an even number, right? So the first thing to do is you're gonna have to figure out a way to put them, turn them into a square. So what that means is you're gonna have to add in some blank columns. That's one way. Or the other way is you draw some random numbers and you treat that as a new column. Is doing any of these gonna increase your performance? We don't know yet. If you're doing, if you're adding 0 valued columns, chances are it should not affect what you're doing as if you haven't added them. Okay, so if you're just adding 0 value columns, that shouldn't really give you any information. It shouldn't really damage your performance either because they're 0. However, if you're adding noise, then anything can happen. Okay, it can be good, it can also be bad. All right, so we're going to talk about both of them. What that means is you're going to be like, you say, okay, here it's my x1 all the way to my x7, and I can't really put them together. So what you're going to do is this. You say, okay, let me put them in a square, right? x1, x2, x3, x4, x5, x6, x7. And then you have 2 blanks. Then you can't do anything, right? So you're going to be forced to add in some numbers here, x8, x9. And then x8 and x9 are all zeros, right? You're allowed to do that. You just add more columns as zeros. Anybody can do that, right? You go to Excel spreadsheet, you just enter 0, you just copy paste the entire column, okay? Then you have what? You have 9 columns, right? Not 7, 9. 9 means what? 9 means 3 by 3, right? So now you're in this nice shape that's 3 by 3, right? 3 by 3. And then you're good to go, right? You do your usual convolution operation and so on and so forth. The only problem here is, A, you can't really explain what convolution means here because they are not image objects, right? It's not like there's a weird shape here that somehow the information is preserved there, right? You can't argue with that. And as a matter of fact, even if it does, you still don't know that truly is the case, right? So think about it. If you have like some sort of regression problem, right? Let's say this is a number of bedroom, and then this is like square footage of the house, and then you're trying to predict house price, right? How do I explain to somebody else that the number of bedroom and square footage have to be next to each other, right? There's no such thing as okay, this is number of bedroom and this square footage, they have to be together. There's no such thing, absolutely no such thing, right? However, if you can convince people, you say, okay, well, you look at the correlation and it turned out that these 2 columns have high correlation. Okay, so then maybe there's argument. Okay, then what that means is you need to go to look for the columns with high correlation, right? Let's say 1 and 5 have high correlation. Then what you're gonna do is you say, okay, let's pick that, and then let's put them together, x1, x5. Maybe you have a shot there, okay? And then you say, well, x2 and x6, they have high correlation. Okay, then what that means, if you do something like this, that's not going to work, right? Because think about it, when you do the rolling window motion, the x2 and x6, if you put things this way, they will never be covered in one kernel, right? Because a kernel is 2 by 2. You do it here, you do it here, you do it here, you do it here. Like these two locations will never overlap. So that's a problem, right? So you can't just put it anywhere, right? You have to put them next to each other. So there are lots of ways you can do. You can erase that. You can say, okay, let me put x6 here, or you can say, let me erase that. Let me put x2, x6 like this, right? So all of these are judgment calls that you're gonna have to try out. That you don't really know which one's right, which one's wrong. Does that make sense? So this is what the small caveat is. That's essentially what this is. So the short story is, yes, you can do CNN on other data sets that's not image, but, right, there's a but you lose the interpretation and you have no idea how to tune it, right? Because you can't explain to people why these two things have to be together, okay? And you can only take shots. You don't really have a theoretical explanation. So that's just a side story that I want to show all of you guys. Because I know some of you guys are not doing image, some of you guys are. You know, maybe I want to point this out. So hopefully everyone's on the same page with what's happening here. All right. So with that being said, now let's talk about convolution operation. So on a high level, this is a key concept here. A convolution operation is essentially an element-wise matrix multiplication. So I'll write that down. This is element-wise matrix multiplication. So what that means is, if I give you A, B, C, D, and then I give you 1, 2, 3, 4, then this is defined as A plus 2B plus 3C plus 4D. Okay, so this is what an element-wise matrix multiplication means. And as a matter of fact, people have this weird symbol that they draw a multiplication sign and put a circle around it. So it looks like this. Exactly like that. So maybe I should really just give a little bit more space. And then I'll just draw a symbol here. And this means element-wise matrix multiplication. Okay, so that's what it means. And then the convolutional layer is essentially this operation many times. All right, it's as simple as that. So let's talk about it. Let's say you have a picture. This is your image, and let's say 3 by 3. So what that means is you have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's your picture. And then maybe you have a kernel, and the kernel is going to be relatively small size, 1, 0, 1, 0. Yesterday we used 1, 1, 0, 0, right? Today we're going to try it this way, just to give a little bit of diversity here. So you do your usual drill, which is your convolution operation. So it's going to be this symbol here. And let me just move this down here, so it's slightly better looking. All right. So now what this means is, when you do your convolution operation, you're going to apply this kernel on the top left corner first. Okay. So what that means is it's going to be here. And once you're done, you rotate to the column, one column to the right, and then you'll be here. And that will finish the first row because you have nowhere to go, right? That's the end of the edge. So then if you're at the end of a picture, you go to the next row from the beginning. So then you put it here, that's the second row, right? And then so on and so forth until you hit the last spot of the original image. And that's really it. This entire thing is called a convolution operation. So you can work out the math one by one, okay? And we're gonna do that right now. So think about it. If you're on a 3 by 3 image and the kernel is 2 by 2, and you do this rolling window motion, exactly as what we discussed, you should really have 4 numbers in the end, right? So what that means is, let's say you work out the math, there should really be 4 numbers here. And then you need to work out what they are, right? And the particular operation is exactly this. So you're going to be doing this 4 times. Okay, so that's the math. So first thing, let's keep it simple, right? First thing, which is the first number, right? We're talking about this number here. So it's going to be what? 1, 2, 4, 5 multiplication, 1, 0, 1, 0. So this is essentially just gonna be 1 and 4 because these two numbers are what you have left, and these two numbers are all zeros. So the zeros then doesn't do anything, doesn't change the result. So you can just say 1 plus 4, this will give you 5. And then with that being said, you can just erase all these in here and you can say 5. Okay? And they do the same thing for the other numbers. What's the next one? 2, 3, 5, 6. And this is going to give you, let me write out a kernel. 2 plus 5, this is going to be 7. So then 7 is going to come here. Okay? And then so on and so forth. I'm not going to bore you guys with all of it. This is 4 plus 7, that's 11. And then number 4, which is last one, is going to be 5 plus 8, and that's going to be 13. All right. So then what have we done, right? So what we said was, well, we have a 3 by 3 that's here. Now after all of these math, we're down to what? 2 by 2, and that's how things work. Okay. And geometrically, okay, this matrix should be carrying almost all of the information from the original matrix. But it's gonna keep some information, but it's also gonna drop some information, right? So the information that it's gonna keep, it's defined in the kernel. And if this kernel, it's have like some sort of like a vertical, like kind of like a stripe on the left, then it's only gonna keep the vertical, like vertically patterned information in the end, right? So if you have a picture look like this, the ones is going to be blocked out, so that's one color. 0 maybe it's going to be another color, right? So that's how this kernel looks like. And if you apply this on the original picture, it's only going to filter through the information that looks like what's inside of this kernel. Okay, and that's precisely what kernel means. It kind of acts like a filter. So with that being said, that's really it about convolutional operation. And then after that, people do a couple of other things I'm going to tell you right now. One is called the max pooling, and the other one is called the average pooling. So this is going to be the pooling layer. Okay, so we're going to talk about this one by one. Right now, what we talk about is called the convolution operation. So I'll write it here. This is convolutional layer. And then also, after that, you have a pooling layer. Pooling layer is even easier to understand. There are only two types. There's a maximum pooling, and then there's also minimum average pooling. Okay, and I'm going to tell you guys both. So where are you right now? You are here, right? You have the picture, you send the kernel through, and then you're down to a 2 by 2 output. So 5, 7, 11, 13, that's going to be your final result. And then you're like, okay, let me do max pooling, right? Or average pooling. So what I look like is the following, 5, 7, 11, 13. So let me copy here, 5, 7, 11, 13. So if you do a max pooling, literally you're just taking the largest number, okay? And then what's the largest number here? It's 13. So that's it, just 13. And then you also have an average pooling. So 5, 7, 11, 13. This is going to be 5 plus 7 plus 11 plus 13. And then you have to divide it by 4. Okay? So average pooling is basically just like what? Taking the average. And here you have 4 numbers. So what's the average of 4 numbers? You add them together and divide it by 4. Okay? So 5 plus 7, this is what? This is 12. And this is going to give you 24, and this is going to give you 36. So this is 36 divided by 4, right? And then it's going to be 9. And that's it. Okay, so these two operations, convolution layer and pooling layer, people use it very, very frequently. Almost everyone uses these two layers, disregard what neural network they're building. Okay, it's actually like after like 10, 20 years of development, something we kind of forgot about it, something we still held on. these two things are something that we still held on. Okay, because these two methods are what's considered the key methods to tackle the invariance problem, the invariance property problem. And not necessarily solve it, but it's like one good way to tackle it. Okay, and that's essentially what's led on to like the next 10, 20 models that's essentially been building a foundation of what we are for today's computer vision. And almost all of the computer vision problem or project have something to do with these two operations. So these two operations you're gonna have to know. Even it's as simple as this, you have to know this by heart. So that's what I want to say. And then since this is data science, right? This is obviously more of art than science. So I'm gonna repeat the sentence again, and you guys are gonna hate it. All right. This is still gonna be a trial and error procedure, and the trial and error procedure in these two layers specifically coming from the kernel. Okay. So we're talking about this thing here. All right. So from yesterday, we saw that there are different types of kernels. Giver filter, that's a particular type of kernel, right? And then there are like some sort of other filters or kernels. You can essentially do whatever you want. So when I was doing my PhD program at Columbia, I was actually focusing a lot on this particular kernel problem. And based on my research, I actually don't think people know what that is. People actually don't really have a solid understanding of why we want to do things this way. They know that if you do things this way, you're gonna get certain features out of the picture, but they don't really know why. Okay. So that's kind of one issue here. If this is something you guys are interested in, definitely let me know. We can definitely turn this into like a decent paper. But anyway, so the problem is basically on the kernel thing, right? So there are two issues. The first issue is what kernel do you use, right? So let's write that down. Two problems. All right. So the first one is what kernel do you use? What kernel to use? So what this question is asking is, sure, 2 by 2, fine. But what are the numbers, right? Why does it have to be 1 0 1 0? Like, why can't it be 1 2 3 4? Why can't it be like 1 5 3 7? Well, you be me, right? Turn out we don't have an answer. You use whatever you want. Okay. The second is the number of filters. Right? So what kernel to use? And the second question is how many kernels do you want to use? So let's write that down. How many to use? Okay, it turned out we don't have an answer for that either. No one knows. Right? No one knows. It's a what is it, like 100? It's a 200? No one knows. Okay. People tend to use kernel number that's like a power of 2, right? What's a power of 2? Like 2 to the power of 1, that's 2. 2, that's what? 4, right? 2 to the power of 3, that's 8. And then 2 to the power of 4, that's like what? 16. And then so on and so forth, right? And then eventually you're going to get 32, 64, 128. What's next? 256, 512, 1024, 2048, and that's it. So typically, people tend to pick a number from this list, okay? These first couple of numbers probably too small of a kernel size. It basically means, okay, whatever kernel this is, let's just all put our faith in it, right? If you pick this the two kernels, then basically what you're saying is, okay, I have such strong faith for these two kernels that everything happening in the world can be explained by these two kernels. That's of course not true, right? So typically people don't like to use a small number. But then think about it. The other way is also not going to happen, right? Okay, why don't we just go crazy on the number of kernels? I forget about 2048. Why don't we use a billion kernels? Right? Why can't we just use a billion kernels? Well, your computer doesn't allow it, right? You're going to run out of memory. So once again, this is like a sweet spot in between that you're going to have to find. You're going to have to find the sweet spot such that it's not that small, it has decent amount of size, and it covers a good amount of information, right? There are kernels that's detecting circles, there are kernels that detecting diagonals, There are kernels that detect in square. You have to find them, right? Whether that number is 8 or 16 or 32, no one knows. It's completely dependent on what data you are using. All right. So you're gonna have to start from like 32, and then you go to 64, and then 128, and then 256, until to a point that your computer crashes. And that's gonna be the range of your tuning range, and you're gonna have to try all of them. And then whatever works in the validation set, in the test set, that's gonna be the number that you use. Okay. So as stupid as that sounds, that's unfortunately how people still work and how people still trying to figure out these two questions. Does that kind of make sense? So I just want to lay that out there. Some you hear social media talk about how terrifying AI is. It really isn't. End of the day, it's just really about trial and error. And trial and error really comes down to if it's too little, if the number is too small, you don't like it, doesn't solve a problem, no complexity. But if the number is too large, your computer doesn't allow it, you run out of memory, your computer crash. Okay, so then that's the range we're in, and then you tune it in that range. And it's as simple as that. So I just want to toss this out there because I know that in the past, some people do their projects and maybe they find some images on Kaggle or some other source that they are processing it together by themselves, right? Processing the data by themselves. So what that means is you can look up a paper online, you find some source code online, and then you spend like all your energy, and then you finally plug the picture inside of the source code, and you get some results, and turn out the results is bad, and then they kind of feel discouraged, right? So usually when that happens, I will come back and will check. Okay, first of all, how do you process the data? If you process the data in a different way than what the paper says, then of course you plug it into the model, it's not going to work, right? Because the model is not built for your data. Disregard how you process it. The model is built for something else. Okay, so that's something that truly you have to pay attention. Every CNN model, and this is as stupid as it sounds, every CNN model solves one particular problem. I have not yet seen one CNN model that solves all the problems. I wish that's the case. Then it's simple. We can just spend one day. I'll teach you that one model, and we all go home, right? I wish it's that simple, but it's not. Okay, it's not. It's always going to be a trial and error, and you're just going to have to try. All right. So usually when it comes to like a performance issue, I'm doing this at my job as well. Usually when it comes to performance issue, go back, check your assumption. Okay. Whatever paper, whatever model in class that we talked about, or you see from your class in the future, or you read a paper, whatever, right? Whatever model that you see that people claim, high performance, 90%, please check the assumption. The assumption means what? The assumption means what's the size of your picture, and then how many kernels you use. And if you use kernel, what's the kernel size? 2x2 or 3x3, right? And then how many pooling layers do you use, right? So these are good things to check. If you miss any of those spots, okay, if you miss any of them, then chances are it's not going to produce the same performance. That final result is going to change real fast. All right. So this is something I want to mention to you guys, and don't get discouraged either. Just like other sciences, in what we do today, it's not there's no Bible here, there's no cure here, right? It's not like I teach you this and then magically it works for everything. So that's definitely something I want everyone to be on the same page. And then also for debugging purpose, if something happens, these are the spots to check, right? You gotta go back to each layer, go back to each operation, and then you gotta challenge your own assumption. Okay, so if you make any assumption, it can be as simple as, hey, I'm putting this together this way, right? It can be as simple as that. Well, why do you want to put things together this way, right? You are able to do that, but it doesn't mean that's the correct assumption, right? So you gotta challenge all this when you build a convolutional neural network. And I can tell you based on my experience, the most advanced data scientists or the most experienced data scientists out there, they usually, the coding is not their strongest suit. I'll tell you this, coding is not their strongest suit. Their strongest suit is they have a sharp eye to detect what's wrong in the pipeline. Okay, so what that means is it kind of feels like, how do I explain this? It kind of feels like you're reading a poem, right? and then there's not one word that you just you know that it doesn't work, but then a good poet is they kind of tweak one word, and then it's like a world-class poem. Where if I'm writing a poem, then it will never be a world-class poem. The sentences are just all wrong, right? Even if I have a good idea, I probably won't be able to tweak the words in a way that it becomes a good poem. So in data science, it's kind of also like that. Whenever you have a model and you have an idea, the experienced data scientist is able to pinpoint a spot in the middle, such that the data, the updated model is tuned into the data much more efficiently. So that's where experience comes in. And that experience, I don't think it comes with textbook, to be perfectly honest. That experience comes from how much time you spend with the data. Just plain and simple. Okay. The best example I can give you guys is this. People have been doing natural language processing on annual reports many years now. Okay, and we have very powerful machine that essentially the same machine, the same model that's playing the Go chess or doing the Watson. It's like a Q&A machine that's going on Jeopardy and answer questions. We have all these advanced machines, and it's probably the best that we can build for today. You have them read the annual reports, and they can never duplicate Warren Buffett's decision. Never happen. Okay, so what does that mean, right? So Warren Buffett is kind of considered the best of us that is able to process years, decades of annual reports and make a final decision. You buy the stock or you don't buy the stock, right? So far, no machines has able to produce that results. And why is that the case? It's because there's something that Warren Buffett is able to pick up that has been in his experience for so long, and he's already tuned into that data set. He's looking at data set for so many years that no one is able to benchmark that. So then in that case, what that means is these annual reports is kind of like his it's kind of his hand, and he knows his hand back and forth, very familiar. So he no longer needs a machine to do that, right? So a good data scientist kind of feels like that. You should not need a machine to help you identify what the pattern is. And then you know coding, you happen to know coding, you happen to know Python, and then you have a machine to come in here to deal with that result. So that result doesn't belong to you only, you can share that results. That's the correct way to understand this entire field, okay? So I don't want people to finish today's class and be like, oh yeah, AI is destroying mankind, all right? That's never gonna happen, all right? These images are here. Sometimes people use them in an incorrect way that takes advantage of other people. Of course, that's not an AI problem, right? That's an ethical problem, okay? So we're going on a tangent, but I just want to let you guys know. It all comes down to what? All comes down to your assumption of data and your domain knowledge. So a good data scientist needs to have both. All right. So that's kind of what's going on here. All right. Any questions so far about convolution operation or about pooling layer? Any questions? Let me check the chat. All right, there's no questions. Okay, so I think we can jump ahead to talk about the code a little bit. It's going to be quite interesting for today's material, and I'm gonna give you guys a little bit more in regards to convolutional neural networks. Hopefully, this can help you guys with your data science projects. So bear with me. Let me find the code, and I'll share my screen. All right, let's share my screen. Cool, it should be coming up. Can everyone see my screen? Good? Awesome, thank you. All right, so we are talking about, I'm in the tutorial folder, by the way, and this is exercise with deep learning, so EXDL. And these are all the reference code. So when I pull code or when I talk about something using Python, this is what I'm drawing code from. So today I want to give you guys more in terms of CNN. So that's going to be exercise 4. All right. So we started this yesterday, but we haven't really finished it, right? We talked about convolution operation. We walked through this math again today, and same with average pooling. And then after that, I think we can start jumping ahead and talk about the code. This is fully connected. We already talked about that in neural networks. So there isn't really much to be said. Just you make sure that every neuron between layers are all connected. That's essentially what fully connected means. All right, so let's talk about the code. So this is the code that we're referring to, okay? And for those of you who are curious about this field, this model is actually taken from the original paper by Yan Le Kun, okay? The original neural network is called the LeNet. And for what he's doing, he actually only had 2 convolutional layers. So what that means is in his model, he's having a picture coming in. He has one convolution, he has a pooling, another convolution, another pooling, and that's it. Okay, so what does that look like in Python using TensorFlow? So you have your sequential API, you set it up. Name of the model, you can call it whatever you want. So this I'll leave to you. First thing is com2D layer. Okay, everything else I trust you guys will figure out. The only thing I want to mention is the input shape. This input shape must be exactly what your data has. Okay, I'll give you an example. Let's say, suppose your image data has dimension, and I'll type out a number. Let's say some number here, 60,000, and then 28 by 28, and maybe by 3, right? This means that you have 60, is that 60? 60,000 images. Each image is 28 rows and 28 columns with RGB channels. So this is your color channel. That's why you have 60,000 by 28 by 28 by 3. Okay, so if you are this dimension, then you better set your input shape to be the dimension of each picture. So it's going to be whatever excluding this 60,000, all right? So I'll say hence, you should set the argument input shape to be 28 by 28 by 3. And notice that this is a parenthesis, is a tuple, right? So this has to happen. If something is screwed up here, then the model is going to crash. It's not going to work, okay? So that's one thing I want to mention, which is here. This input shape has to be the dimension of your picture, and doesn't count the 60,000, okay? It's whatever coming after. If you have one color, then it depends on how you process your data. So let's write that down. Technically speaking, this is one paragraph, and let me open a different paragraph. So I'll say if you have one color only, let's say it's a grayscale, then it depends on how you process the images. The recommendation is instead of killing this dimension, you leave this dimension, you just set it as 1. So I'll write down what that means. The advice is to reshape dimension into 60,000 by 28 by 28 by 1 instead of 60,000 by 28 by 28. In this case, you can set the argument input shape to be 28 by 28 by 1. Then this way you won't be able to mess up. Okay. I can tell you this. Every year when I teach the same topic, it doesn't matter where the student come from. Could be young, could be old, doesn't matter. 30% of people make mistakes on this particular thing, which I think the problem is not in neural networks, which I think the problem is really in the data structure and the data types. Because people have problems understanding, well, what does this mean, right? Here, I'll show you an example. if I give you a NumPy array, I'm going to import NumPy as NP. So that's my library. And then I'll show you, let's say, np.ones. So I'm creating something that's just all number 1, okay? And I need to give a tuple, I give a shape. So let's say 3 by 2 by 2. So what that means is going to give me 3 matrix. Each one is 2 by 2. Right? I'll repeat that again. 3 matrix, 1, 2, 3. Each matrix is 2 by 2. Okay? So if that's the story, then what you're going to do is you should be able to reshape this. Reshape into what? Into something by 1, right? That's not going to give you an error. You're actually allowed to do that. 3 by 2 by 2 by 1. So it's going to look like that. Now, this may look weird, but it's actually the recommended data types, or how do you say, dimensions or shapes, that you could send that into the convolutional neural network. And the reason I say this is because sometimes you might be able to, you might have to slice a color out of, slice one color out of a color image. And how you slice it is you work on this dimension here. So you're better off just leave like that in the beginning, so that in the end, everything works out. And if you want to slice it in the end, no problem. Versus if you don't leave this at all, you don't do a reshape, and you just leave as 3 by 2 by 2, then you can't slice that, okay? Like this way, you can't slice it. Right, so that's kind of like the difference. It's not a whole lot of difference. Technically speaking, they're the same thing. But this dimension is going to be trying to match. And if you can't get a match, then this code is going to crash. Okay. So that's one thing here. Everything in the middle, I trust everyone will be able to figure out. Filters, that's the number of those small kernels that we use. Each kernel has a kernel size. That's, of course, once again, depending on whatever you want, right? Typically, people start with a small number, and here small means 2 by 2 and 2 by 3, right? Unless you have assessed a picture that the pattern like magically cross like half of an image, then maybe you have an argument. You say, okay, well, 2 by 2 and 3 by 2 is too small for me. I'm gonna use like 5 by 5 or 6 by 6. That's fine. But before you look at the picture and before that happens, typically the default setup is 2 by 2 or 3 by 3. Okay, so recommendation here is this. The recommendation here is when you're loading the image data, you have no idea how it works, right? You don't know it's accurate, you don't know how good your model is. So you set up a default one, you just run it. And then you look at the performance, you're like, okay, that's good, that's bad. If it's good, then fine. That's good to go, right? If it's bad, then you're like, okay, let me look at the picture again. Let's see what's going on. Aha, some patterns are covering like half of a picture. So 2 by 2, 3 by 3 is too small. Let me change a big one. Okay, so that's what's going inside of this intuition here. It's not a, it kind of, the tuning here, when I say tuning, people think about try 1, it doesn't work, try 2. Try 2, it doesn't work, try 3, and so on and so forth. Yes, that is tuning, but that is essentially saying, okay, let's give up all human intuition and let's tune this complete from scratch. You can do that, but that's going to waste a lot of time, right? We don't have time to waste. We're talking about Friday as a delivery time. So my recommendation is look at the picture first. You look at the picture, and the picture should be able to tell you a good amount of things. And look at the picture in particular classes. You put them side by side, and then you look at them for that class, and then you're trying to just, in your head, trying to draw some conclusions. If there's a certain class, then what is a common pattern in all of these pictures? And you can kind of look at the size of the picture and you say, okay, how big is that, right? So I'll give you an example. Let's say you have a picture here, and then you have a face of a cat that looks like that. That's ears, that's eyes, that's whiskers, right? And then if I tell you this is like 100, and then this is also like 100, and then your goal is to get the ears out, right? Your goal is to get the ears out. Then this area, you can kind of get a guess of how big that is, right? If it's 10, if it's 8, right? You can get a sense of how big that is. Does that kind of make sense? So this is kind of where you build up that intuition. And then, or you can zoom in and go even on detail. You say, okay, here is probably too big of a pattern. Let's just do a diagonal. And then you can kind of get, okay, that's probably 3 by 3 or 4 by 4. And then these are the numbers that you use to change here. Okay, so that's kernel size, right? Filters, there isn't really a whole lot of science going to filters other than it's a 2 to the power of an integer, whatever integer that you like. Typically, it's a 32, 64, some people do 128, but that's kind of like the number that I've seen so far. If you go too large than that, then chances are you're probably going to run into overfitting area. I don't know when it's going to run to overfitting area because that kind of depends on the data. But eventually, you're going to run into overfitting area. So that's also another way for you to keep track on that. All right, so that's the convolutional layer. And then with that being said, I think you're kind of good to go, right? You have dense layer. This part is exactly the same as when we talked about before. In neural network, in artificial neural network, it's exactly the same. And then I think from there, you're good to go. You can just train the model, do a compile, and then you do model.fit, and you can just train. Okay? So with that being said, that is everything about convolutional neural network. We're going to take a quick break, and then it's going to be 10 minutes. And then when we come back, we're going to talk about a little bit about transfer learning, and I'll let you guys on the breakout. So I'll see you guys in 10 minutes. All right, it should be recording. All right, so do a quick recap. So what we done in the previous hour is we say, hey, look, we want to use convolutional neural network, and we look through this code, and there's a 2 convolution layer, 2 pooling layer. They're kind of back to back, and then after that you flatten it, and then you do a dense layer. All right, and since this is 10 classes, obviously you can do a 10 class classification. So we're assuming that it's a classification problem. The only thing that you cannot change, or you don't really have a freedom to change, is the input shape. That depends on your data. And the output shape, 10, that's the number of classes that this data set wants you to predict. Okay, of course, you can define that, then you don't have to redefine the data. But the beginning and the end, that's dependent on your problem. Once you have a problem, once you have data, the beginning and end of the model is done. It's fixed. You cannot change that. Okay. Anything in the middle, you feel free to do whatever you want. All right, so that's the story. With that being said, I already went through this code and I quickly do a tuning. It turned out that the model starts with 1 epoch, it's about 41%, and it keeps on training, and then eventually, when you get to 50 epoch, it's at 66%. But then notice that what's going to be a problem here is if you scroll up and you say, hey, 41, 49, 52, and then when you get to somewhere here, that's about 8 epoch, right? 8 epoch, 9 epoch, you're going to start seeing 60%. And then you're going to get to 62%, 61%, and then eventually just up and down, and then start flattening out. And when you start flattening out, it's flattening out around 67%, 68%, and then it basically stayed at that range for the rest of the training. Okay, so that's going to be a problem. And I know that's going to be a problem because if you look at the training performance, the plot on the left, that is the loss. And there are 2 lines for the loss. One is a blue one, that's a training set. The other one is the orange one, that's the validation set. If your training set loss is keep going down, all the way to like almost close to 0, right? Whereas your validation set loss, it's first going down, but then come back up. That's called overfitting. Okay, so overfitting means exactly this pattern. They both go down, but then eventually they start diverge. Okay, one go down, one go up. That's called overfitting. So overfitting is a problem because what that means is I look at my training data and it looks like it's like somewhere here, and that looks like a small loss. So I thought it's doing a great job, right? But it's not actually that good of a model. Your model should just be wherever it's here, that the orange line maybe flatten out a little bit, and that's the best model. Okay, so this idea can be confirmed using the accuracy plot on the right. So it's the same idea, and you probably see a similar pattern, right? The blue line is the training set accuracy. The orange line is a validation set accuracy. So they both go up in the beginning, and then eventually they diverge. Training set keep going up all the way to like 100%, and a validation set go up first, but then start to flatten out, and then wherever it's flattened out here, that's about 67, 68%. So then you know that somewhere down the road, you're probably overfitting because your training set is at almost 100%. And if I give you a picture, guess what? You're not at 100%, you're at 67%. Okay, so that's why this difference is important. You can't just like ignore that, right? That means your model is hitting a bottleneck. Then you either change the entire architecture of your model or you go to a different model. Okay, so with that being said, if you take a look at the performance and you're like, okay, accuracy is oh my god, 97%, that's great. Well, that's not the case because you look at the validation set accuracy, it's only at 66%, 67%. And you can do a model.evaluate, and you throw in a test set, and the final accuracy is just 6%, 67%, and that's probably as good as what a validation set is doing. Okay, so this is the confirmation to tell you guys that whenever you're looking at how accurate your model is, or whenever you're checking the performance of your model, please use test set. Okay, and here is a demonstration of why that's the case. If you don't use test set, you use the training set, which is this number here. You're going to be like, okay, my model is doing a great job, it's at 97%. But then in reality, it's at 66%, right? So that is going to be exactly what's going on. And the reason I'm saying this is because in your presentation on Friday, it doesn't matter what you're doing, but whatever it is that you're doing, please make sure the whatever percentage that you tell us is the final result is on the test set. Okay, this is important. Please do it on the test set. So this way we know that the performance is robust, and if I give you a new set of data, we can trust that results. Okay, so that's the story here. If you look at this graph, you might be like, well, how do I know like this is the case, right? Like, how do I know it's gonna stop at 20? How do I know it's gonna stop at 30 and then it bounce back up? How do I know that? You don't know that. You're gonna have to work it out. You're gonna have to try 50, and then you see that it goes back up, and that's how you know. But before you try 50, you're never gonna know that at 20 or 30 it bounces back up. Okay, so far, this kind of pattern, there's no way to tell, oh yeah, 20% is gonna start bouncing back up, right? There's no way to tell that. So the name of the game is, well, do you like keep on training, or like when do you stop, right? That's kind of like a question. Like, you can't tell, then how do I know how to stop? So my recommendation is typically to give like a large number first. Of course, the trade-off is you're gonna have to be a little bit patient with the training, right? Large number means what? Large number means you train a little bit longer, right? So spend more time, right? That's the trade-off here. So you wait a little bit longer, you see what the performance can do. If it keeps going down, then you increase, right? And it still keeps going down, then you increase more. Until a certain point, it starts bouncing back up, then you stop. So typically what people do is they train this graph incrementally. I'm going to start with like maybe 5 epoch. I see that it's going down. Great, keep going. 10 epoch. Maybe it's still going down. And then 15, and then 20, and then 25. At 25, you should be able to see that this thing is flattening out a little bit, right? And then at 30 or at 35, you should be able to see that this thing goes back up. And then you can say, okay, let's just stop it, right? That's kind of how things work. There is another function here. I don't know if I have it here. Let's see. Yeah, so there's this function. This is a callback function here that some people find handy, some people don't. But I'm going to tell you guys anyway. So this callback function is called model checkpoint. This model checkpoint has an argument called save best only. And all you gotta do is define this callback function. You just define this whole thing, throw that in the bracket. That bracket is important, right? Throw that in the bracket. And then you call it callbacks. And this callbacks, you're gonna have to put it physically in the model.fit as an argument. So you do this, and then add a comma. This is gonna be where your argument is. If you set this callback function up, it will automatically save the best model. So you can let on training for 200 epoch. You go grab a cup of coffee, right? And then when you come back, it's automatically gonna find the spot and then save that model. So people might find that a little bit helpful when you're like maybe a little bit busy, right? For me, if I have like 5 notebooks open, I will really find this helpful. But sometimes I want to do things by hand just to get a taste of how the model learns and what the data does. Then in that case, I do it by hand, so I don't use it. But if you have like a multiple notebooks open, then feel free to use it. Okay. So that's what I want to say about all the building blocks in convolution neural network. The next topic is going to be transfer learning. Transfer learning is super simple. I don't think we're going to go through the entire script. I'll just quickly hint on the key concept, and then we'll let Sam to put you guys in the breakout room. So the idea of transfer learning is saying that, well, if you look across the board and look around the images that we can see and the common objects on the street, cats, dogs, cars, planes, trees, right? These common objects, chances are they share similar pattern that if the model has already learned, then why do we have to throw the model away, right? Why don't we just respect the model and keep on training using the original pre-trained weights, right? That's kind of the idea here. So you can do that. And as a matter of fact, people almost always do that in the industry. No one, and I want to repeat this again, okay? No one is training model from scratch. Unless you have some sort of a data set that you have no clue what the data set is doing. And no one else has done it before. And you're like actually creating the data yourself. Even that, you can probably still find some sort of model before that you can load up the weights. But let's say that's the case, right? The pictures that you are analyzing have some sort of overlap between previously published paper or model. That's going to be an area where you can use transfer learning. Okay, transfer learning sounds complicated, but really what it means is the following diagram here. And really, the difference is how you navigate through that prior knowledge. Okay, so how does it work? Conventionally, you have a data set 1, you build a model, right? You call it machine learning model 1. And then you go to data set 2, you build another model, machine learning model 2. And then so on and so forth, 3, 4, 5, right? As you can imagine, this is going to take forever, right? What if this machine learning model is like 20 layers, and you're going to have to tune them layer by layer? Then this is going to blow up really fast, right? And then every model is going to have to spend weeks to train it, right? That's crazy. So what people find helpful is if you're doing data set 2, why don't you find a previously existing data that looks similar, right? And then there's a model that's published online that already learned that everything that there is that can be learned in the first data set. Then let's use that model in your current pipeline. That's it. That's what transfer learning means. It's transferring the prior knowledge and learn from there instead of learning from scratch. Okay, that's what transfer learning means. So all of it sounds straightforward. How exactly do you do that, right? There's a function here that I'm going to show you. This big function here called create model function. What transfer learning really carried down to, boggles down to TensorFlow is really to navigate through these applications. So in TensorFlow, the good thing is there's this library called TensorFlow Keras applications. And these applications has like a list of previously well-trained model that's essentially free online that you can download their weights. Okay, so you can download their model, you will load up the weights, you toss your picture inside of it, and then you train from there. Okay, so that's what transfer learning means. So that's kind of what I want to say for now. We're gonna put you guys in breakout room because I really want you guys to get project started, and I'm gonna send this code to the Google Drive for the class, and then we'll come back to this tomorrow. And if you have questions, we'll address them one by one. Okay, so Sam, why don't we have the breakout room open, and then whenever you see the link start on your screen, just feel free to click in, and then start talking to each other. Get a project started. All right, so yeah, I can stop recording.